Okay, so I'm going to be talking about the vector extension proposal. Wow, okay. Let's just zoom in there. So vectors are near and dear to my heart. It's something I've worked on for a long, long time. And sometimes I feel that we had to do RISC-V in order for people to get to use vectors. And actually the V was kind of a pun when we did this initially on 5 and vectors. Anyway, so let's dive in here. So what are our goals here? The goals for the RISC-V, and this is going to be the standard V extension, efficient and scalable to all reasonable design points. So both low cost and or high performance designs, and different kinds of microarchitecture, in order, decoupled, or out of order. Support integer, fixed point, floating point data types as well. Should be a good compiler target. We want to support the two main kinds of data parallel programming models, the implicit auto-vectorization through things like OpenMP, and also explicit SMIMD style programming through things like CUDA and OpenCL. Should work well with virtualization layers, so play nicely with the rest of the OS. And one of the goals with the standard V extensions, it fits into the 32-bit standard encoding space. But to be a base as well for future vector-based extensions. So don't do everything in this first one, but design it so it will work with later extensions. One non-goal is to look like everybody else's packed SIMD extensions. Well, the non-goal is to look like a GPU, right? So this is an honest-to-goodness vector coprocessor. And how many of you know what a traditional vector machine looks like in a programmed one? Okay, how many of you have programmed with SIMD instructions? A lot more, okay? That's what I suspected. All right, so now packed SIMD has a long history, and in fact, this is a example of 1950s architecture. So this is actually Ivan Sutherland at the console of the TX2, which was one of the first machines to have packed SIMD instructions. We want to dive ahead to the 70s, vector-style machines. If nothing else, they had snazzier suits there. So here's Seymour Cray wearing a nice suit there. You can't see it here, but it has piping on the edges. Very cool. The machines look better too. So this is actually the architecture of the TX2 packed extension. It had 36-bit words. You could split into 2 18-bit or 4 9-bit. And in fact, you could also do 27-bit and 9-bit as well, uneven splits. And this is the vector machine. Okay, modern day GPUs. Well, GPUs are these things, are these very weird things. Having worked in vectors a long time and seeing GPUs appear, it's very strange to see these beasts because they're very odd. They're kind of these discrete accelerator running in their own memory space. They're kind of like an old attached processor. More recently, they've been trying to give more equal access between the GPU and the CPU memory, sharing the physical memory, and then more recently trying to share the virtual memory. They're not still quite at the place where you can take a page fault on a GPU operation, so it's still kind of awkward to use. They're terrible at scalar code, so you do that on the host CPU. And they're really only effective in very large data parallel tasks, tens of thousands of elements. And the ISA kind of evolved from this graphic shader needs, and so don't really make sense at all. They're trying to make them more general. And they really only seem efficient if you compare them against Intel's out-of-order cores, right? Otherwise, they're really terribly inefficient compared to most data parallel engines. Contrast to the traditional vector, it's basically the coprocessor running right there next to the scalar processor. Is tightly coupled. Like the Cray one was, you use the vector unit if your loop count was 2 or more. That's a very simple compiler target, right? So if you're doing more than a second trip around the loop, you should be using the vector unit to do it. That's kind of what we're going to get to with the vector extensions. And the ISA evolved from general computing needs as opposed to graphics. And it's very efficient, so it's a lot more efficient than the classic GPUs. So the rest of the talk, I'm going to sort of go over quickly again why traditional vectors are better than packed SIMD or GPUs, and then specifically what we're proposing for the V extension. So I'll start off with a little example, which is this Saxby code example written in a way you would program a machine that had auto-vectorization. So you just write the loop, maybe with an annotation possibly, and then it just gets automatically vectorized for you. Okay. Now, if you're doing this on a packed SIMD architecture, this is kind of what the code looks like. So I'll just step through this assembly code here for a mythical packed SIMD machine. Here's the function arguments coming in your argument registers, A0, A1, and so on. The first thing you have to do is, so Saxby is a scalar AX plus Y. So you have to take that scalar operand and splat it across all the 4 elements of the vector. So now you've copied it into 4 positions. So, that's just overhead. Then you start into the strip my loop. You load 4 elements from one vector into the fixed register. You load 4 from the next. Then you do the actual multiply add operation. that's doing the compute work, and then you store out the result vector, then you increment the address pointers and go around the strip mine loop and handle groups of 4. When you're done with groups of 4, you then have to handle the edge cases, which is the remainder of the things that didn't fit into those groups of 4, right? It's a very simple story of how you do the Saxby on a packed SIMD. Then your vendor comes along and says, hey, we got the next best thing, it's wider packed SIMD. Here you go. So what happens then? Well, you have all new opcodes. You have all new opcodes to do 8 wide, right? So, and I forget, part of the 2 instructions per month that Intel has are to do with the SIMD extensions. They sort of arrive in, the trailer loads every year or 2 when they widen the SIMD extension. So now you have a new instruction, which is load 8 at a time, et cetera, right? So you rewrite all your code now, or recompile it. And one thing to notice as these vectors get wider, the times you spend in the edge cases go up, because you're handling groups of 8, so the non-multiples of 8 are the pieces that are done in the edge loop. Okay. I'll contrast this now with traditional vector style machine. This is kind of the assembly code. Let's step through this. So the first thing is vector machines have a vector length register. This is a great innovation from the mid-70s. And the vector length register you set, the style we use is a thing we call, the way we do our set vector length instruction. It takes the argument, which is the length the application would like to do, and it sets the vector length register to the minimum of that and the supported hardware vector length, and writes that into a scalar register, so you know how many is going to be happening this time around, right? So in this case, the scalar register T0 has the number of elements that you're going to be doing this time around the strip mine loop. A0 is the number of elements that the application wants to do, the vector length. So you set the vector length, you load the 2 vectors, you then do the multiply add, and again, notice you have a scalar operand it's a scalar multiply add, so you just take the scalar register and use that as an operand. You don't need to splat it anywhere. You then store it back to memory and do the address pointer updates, and then do the strip mine loop. No, there's no edge cases, right? It just handles however many elements there are, that's it, you're done, right? Okay, let's turn around and look at a different programming model, SPIMD style. So SPIMD is where you have to do more explicit work, and this is a classic model that's reappeared now in the guise of CUDA or OpenCL. You basically have to do all the work you did for auto-vectorization plus break things up into even smaller chunks. This is harder work. And this is a sort of classic model. You have a compute kernel that's run on each element, and then you say how those elements are distributed across the total application array. Okay, so you kind of break things into big blocks, send those task blocks off, and have the code for each task block runs. And the mental model is every single element in this massive data parallel array is running its own little independent program, right? So that's the explicitly parallel thing. You've distributed the work across a big parallel array and written code for each one of those elements. Now you have this explicit thread element identifier, the TID, thread ID, in these programming models. And you need to do an explicit check to see if you're active, right? Because a thread blocks you send out a sort of some fixed size that doesn't necessarily match your problem size. So in every one of those work blocks, you're saying, am I part of, am I supposed to be doing anything? And if so, then go ahead, otherwise skip over the work, right? So now I'll turn to how this runs on a GPU or /SIMD architecture. I'll pick on an NVIDIA style architecture, as it's pretty common, and they kind of push this programming model first. So you have a bunch of microthreads in your vector. You now think of these as independent elements that kind of run their own scalar program, except under the hood, they're actually executed with SIMD hardware. So the way that this runs now is, first thing, well, you do a branch. Am I supposed to execute this loop, this code or not? I might be off the end of the vector, in which case I should just jump. So you have these branches where it's just there to tell you not to do anything, right? So that's part of the divergence in the control flow is, whoops, I'm not supposed to be doing anything. I'm not part of this block. Okay. Now what's interesting is when they go to load the elements, remember this is just a unit stride load, every element calculates which address it should be using, and then you do a gather. Right, so every element is calculated independent address, independently or redundantly, send it off to memory system. Then you have dynamic hardware coalescing it back together to make unit stride block loads. Okay, and you do that for both of these vectors you're reading in, and you do it again after you've calculated the result. And one thing to mention again, you have to replicate the scalar value across all the elements, so it takes up more register space. Then once you've gotten the result, you also do a scatter to store the result back, and hope that the hardware will coalesce that back to block size work. Okay. So, comparing this now doing with a vector unit, well, vector unit, you don't need an activity branch. You just say I need 3. I don't need everybody who's greater than 3 not to take a branch. I just say, you 3 guys, you do the work, everybody else is off. you get to use a scalar operand, and there's no dynamic memory coalesce. You just load units to write vectors, and they just go to memory. You've told the hardware exactly what you want. You don't have to kind of rediscover this on the fly when you're using a GPU. Okay, another thing is you might say, well, the SMPTE thing, there's some more overhead, but you can run all these divergent control flow kind of SPIMD codes, and well, no, you don't actually. You don't need all that hardware to do that. And if you check out Yonsup's Micro 2014 paper where he showed that on an NVIDIA GPU with compiler support, he didn't actually have to use the hardware reconversion stack to get equivalent performance. So you can handle all the control flow you want without needing the hardware in the SMPTE machine. Okay, so that's why we want to do traditional vectors, better than PackSMD, better than GPU-style stuff. So this is the data parallel extension we're proposing now. And this is sort of in progress. So it's very simple. You start off with the standard RISC-V scalar X and F registers. Those are going to be where the scalar operands come from. We're just going to add up to 32 vector data registers, V0 through V31. And they're going to be at least 4 elements each, where the width of them is going to be variable. So I'll talk more about the details. But you should think of these as being 8, 16, 32, 64, 128 bits. MVL is just the maximum vector length supported in the hardware. And that's actually going to be dependent on what we call the configuration. In addition to the data registers, we also have vector predicate registers, so just single bit per element. And there's going to be 8 of those. And finally, there's 2 CSR registers. One holds the vector configuration. The other one holds the vector length, the active vector length. So that's basically the state that's in the vector unit. Very simple, just vector data registers, vector predicate registers, a configuration register, and a vector length register, right? So that's what we're adding. So there's a bunch of features here. It's not your grandfather's vector machine. We do have reconfigurable vector registers. Actually, this is an older idea from the Fujitsu machines. We're going to allow you to exchange unused architectural registers for longer vectors. We're going to provide a new thing is mixed precision support. So from 8-bit up to max of xlen and flen in powers of 2. So whatever your base scalar ISA supports in terms of xlen and flen, which is the integer width and the floating point width, you're going to be able to go up to that size, variable size in the registers. We want to support integer, fixed point, and floating point arithmetic. And if you have floating point, you have to have the corresponding scalar extension. Doesn't make sense to have the vector unit if you don't have the scalar floating point. The fixed point stuff is going to add, on top of integer, adds some support for rounding, saturation, and scaling, which you kind of need to a fixed point. Unit strides, stride index load stores, and predication. So this is kind of the sort of summary of the kind of features in this extension. Let's go through these. So the reconfigurable vector register file. So we have a limit of up to 32 architectural registers. But in the configuration, we can say how many we actually need. So for a given loop nest, the compiler knows how many architectural registers it needs. And if you don't need all of them, you can trade that for having longer vector registers, right? And so in this little example, I'm saying set the configuration to, I only need 4 architectural registers, right? And if I only have 8 physical elements here. So I'm going to say I want 4 architectural registers, which means my vector length will be 2 in this case. So, V0, V1, V2, V3 are the vector registers. There's only 2 elements each. But if another loop, I might decide I only need 2 vector registers. In that case, my vector length goes up to 4, right? So I've traded the architectural registers for greater vector length. Okay, but it goes even further than that. We have mixed precision support. So the idea here is a lot of applications, you have different kinds of precisions of the data operands. And we can actually subdivide the physical register into multiple narrow registers as requested, right? So the idea here is you can say how many 8-bit, 16-bit, 32-bit, 64-bit, 128-bit width registers I need. So for each register, you say how many bits you need. The machine will then pack all that into the physical register space, right? So in this example, I only need 2 architectural registers, but the second one I only need, say, 16 bits, where the other one is 32 bits. We actually, inside the hardware, will change this around. So now your vector length will be 5. So if you just say, oh, I can actually pack those a bit denser, I only need 5 of them. And what's more, I'll also get the parallelism I get from doing the PackSMD kind of operations, using the same data path, making things wider. So my vector length will be 5 in this case. So the way this looks to the programmer is when you enter a loop nest, you come in with a set configuration and say how many of each you need. Just a convention about the lowest number of registers are the smallest of those and so on. So given the number of each type, there's a mapping from what type each architectural register number will have. And then this is just your strip mine loop with a vector set vector, V set vector length. Here, And at the end, another thing we have is the idea of unconfiguration. So you set outside of a loop nest, you unconfigure at the end of a loop nest, which kind of tells the machine that you're done with a state in the vector unit, and this helps reduce the cost of context save restore. Cray had an instruction X1, which was called vector RIP, which was kind of, it's gone, it's dead, you don't have to worry about it anymore. For us, it's just this vector unconfig. And so in the privilege spec, you'll see there's text about how that is handled in there. Okay. So one other thing about vector machines is they sort of hide not only are you hiding the number of physical bits in your register file, you're also hiding how parallel the vector unit execution engine is. And so you get higher performance by adding parallel lanes. So this is a classic vector machine organization where you have, in this case, 4 lanes, and you just distribute the element positions of the vector across the different lanes. And so all the operations at a given element position only work within one lane. There's no need to copy values between the lanes. So this is very scalable. And when you issue an instruction, it actually goes to a functional unit, say a vector add unit, that's working across all the lanes in parallel in lockstep, right? But all the communication is local to a lane within there. And the nice thing is this is all hidden from the assembly code. You can just scale this up. You don't have to add new opcodes as you scale up the number of lanes in a unit. So this is one of the nice features of vector machines compared to PAC-SIMD and also the current GPUs, that same binary code is going to work regardless of how many bits you have in the physical register file or how many parallel lanes you have in the execution engine. Now, one detail we have to help, the trouble is that if you went all the way down to the vector length to be 1, then even small vectors, you'd have to do some strip mining to check maybe only does 1 at a time. So we had a minimum of 4. So we're going to guarantee that there'll be at least 4 regardless of configuration, vector length of 4, just to avoid that strip mining overhead, right? So in the case you have 32 64-bit vector registers, that's about 1 kilobyte of SRAM. I'll also show the minimum configuration at the end, the whole thing. Okay, so now it seems a bit complicated. You have all these different data types. How are you going to encode this in the opcode space? The idea is we just have this very simple notion of a polymorphic instruction encoding. So we have a assigned integer add opcode. Just have one opcode, and it works regardless of the registers you're putting in there. So each register knows how big it is. So if you're adding an 8-bit to a 16-bit and storing the result in a 32-bit, it's kind of well defined what that means for assigned integers, right? So you just do that. So you don't have to encode different opcodes for all the different data types, different sizes. And similarly, you can encode, say unsigned integer operations, fixed point integer operations, fixed point operations, floating point operations the same way to take operands of different precisions on the input and output. Now you might choose to restrict some combinations to simplify the hardware, but actually a lot of them are pretty easy to support this way. Now the pro of doing this is you get a denser encoding. It's one way of fitting into the small encoding space. And it also eliminates a lot of difficult cases to worry about in the ISA. You don't have to explicitly encode operations to do sign extension and things like that. Some of the cons, though, are you can't reuse a given register to hold different size operands, right? There is a con. And for example, you can't initialize a register from memory with a smaller type. In practice, we don't think this will be a problem, as when you write loops and start doing software pipelining, you typically want to bring it in one size and move it to a different register for the next stage of computation. So we'll see how this plays out. So vector loads and stores, we support unit stride, constant stride, and indexed, classic vector addressing modes. And we have separate integer and floating point loads and stores. And the reason for that is that we want to support internal recoding in the floating point units. That's particularly important when you're mixing different size floating points operands. And the size is just inherent in destination register number. So you configure the vector unit, every register knows how big it is. You don't have to put that in a load and store opcode, right? It just follows with whatever the type is. We also want to support vector AMOs, so vector fetch and add. They're already in the microarchitecture anyway in this case, so you just drive them from the vector unit. Vector predication, another feature, so we have these 8 vector predicate registers, 1 bit per element. We support logical operations between the predicate registers. One constraint of the encoding space is in this 32-bit encoding, all instructions are predicated under P0 by default. And to help out, we have an instruction to swap 2 predicate registers, which, if you're doing an out-of-order machine, actually can be done purely in decode stage to sort of rename the predicates around, to swap the renamings. You have other features for the predication, like pop count to say how many are active in that current thing, and some other instructions that help with cross-element loop optimizations. Some detail to think about, vector predication interacts not so well with vector register renaming if you have an out-of-order microarchitecture. So what predication is, you have to write the old result to the destination physical register, even if you're not computing it in that position. So there's a copy involved. And basically what previously people have done is either that approach, which is, just implies there's another read and another write, even where you're not predicated, or what created in the X1, for example, was, say, the destination has an undefined value where the predicate is false, but then that requires you have separate merge instructions that piece the vector back together again from the defined pieces. So we decided not to go with the more complex one and do number one because it's simpler and safer in terms of properties, verification, and so on. And I think there's a bunch of micro-architectural tricks we think we can do to cut down the overhead if you're doing an out-of-order machine with vector register renaming, to cut down the overhead. So we think number one is easier to spec and safer. So we're going to go with that. One of the source of confusion is at Berkeley we do a lot of vector machines, like many of them, and many variants of ISAs. And you'll see X-Hwacha or Hwacha around. Hwacha is a Korean rocket launcher. So there's a pun on the rocket and doing things data parallel. And it's basically a research vehicle we're sort of pushing the state of the art and in-order decoupled vector machines. Now, we've built a lot of Hwacha machines, and we've done a lot of the RTL design for things like this mixed precision support, so we kind of know how it all works. And the lane microarchitecture is very similar. A lot of its differences in how you fetch and decode and issue instructions. So we fabricated things, so for example, running DGEM, actually running the code with fusible adds 64-bit floating point, we're up to 34 gigaflops per watt, which is, I think, a lot higher than any other commercial chips out there. And we're sort of focusing right now on bringing up OpenCL for Hwacha. And then we'll, V proposal is still kind of tentative. We're still working on this, sort of in the background. So just to kind of give you an idea, if you've never seen how a vector machine is built, here's the vector lane organization from Hwacha, at least one version of it. So the register file is built out of banks of SRAM, one read, one write macros. So very dense storage. And basically you stripe across these to get the operand bandwidth you need. We actually pack integer fixed point ALUs right close to the SRAM banks, so the data is not moving very far, it's just kind of coming in and out of here as we execute a vector instruction. It's only for the larger floating point units, integer multiply divide, that you ship them over to the shared functional units. So just to show you how this works, oh yeah, one thing I should say, we do sort of hazard detection, decode stuff up here per strip of vector operations, and then we just push out micro-ops that go down and execute systolically across the banks. So sort of fire and forget, issue a little control word that drives all these banks to do the right thing. So very efficient execution model. So like these one read, one write banks, the way they supply operands for a functional unit is, the first cycle, you read the first operand from the first bank. The second cycle, you read the second operand for the first operation. Now you have both operands for the first operation. You also are reading the first operand of the second operation from the second bank. And this kind of continues, and now you can execute the first operation and read, then you have both operands for the next one, and so on. And so this way you're kind of striping across the banks, getting all the operands and shipping them to the functional units and back. One operation works like this. Other operations, if you have multiple parallel vector instructions executing, they are striped across the gaps in this schedule. And so you could have multiple, like loads and stores can go in parallel with this operation, for example, reusing those same ports on the same SRAM banks. So it's very dense, very efficient. And chaining just happens naturally because all the elements for a given, all the values for a given element position in the vector all live in the same bank. And so the values are just read and written from that same bank of the SRAM. It's not just constrained to one lane, it's constrained to one bank within one lane. So it's very efficient in terms of data movement also. And so we support, breaking up the physical register file will be packed as necessary for each of the data types. So here's an example configuration with a few different, 2 of these, 3 of those, 1 of those, none of those, right? And then this is the layout. And notice that for element position 0, I guess these banks are 128 bits wide. Element position 0, it's V0 and V1 are here. V2, V3, V4 are here, and V5 is here. Notice they're all different sizes, but all packed into the same bank, so we can get all the operands in and out to an LU that lives in that bank. Okay. So that's kind of the execution, so OS support. The way we support this is we want to support restartable page faults to support virtual memory. And we do this using an old trick from the DEC vectorvax, which is just restart, it doesn't have to be precise, it just has to be restartable. And so they think this will be useful for other co-processors. The model is you just dump an opaque data object. The OS just has to save and restore an opaque data object. It knows how big it is. There's sort of instruction support to dump and reload it. And in the privilege spec, there's other support that helps the OS reduce the number of times it has to actually do that. If the thing's unconfigured, you don't have to save and restore it, for example. Okay, so this all sounds pretty complicated. If you used to, I just want my simple PAC-SIMD unit. Hopefully, the next slide will convince you you shouldn't build a simple PAC-SIMD unit, because if you want to build the minimal V implementation, what does that look like, right? That's the TX2. It doesn't look like that. It looks very similar to the old TX2, but not quite that simple. So you have the standard X and F registers. All you need to provide is 32 vector data registers that are 4 elements wide, right? As big as the largest, the elements being at least as big as the maximum thing you need to support. So that's 4K to 8K bits of state in there. You also need to provide the predicate registers. It's 32 bits of stuff, right? And also the vector configuration register. It's about 10 to 15 bits, depending on what you're supporting. And the vector length, which can be as little as 3 bits. So it's not a lot of stuff to give the minimal implementation of the V, right? Just not many bits at all. And the advantage is that with this and supporting this ISA, the same code will run on something that has, 100 times more stuff in the vector unit. The same binary will run, right? Okay, that's it. Questions?
A quick question on the 34 gigaflops per watt. That was for IEEE double precision?
FuseMol ads, yeah. Okay. Yeah, double precision with FuseMol ads.
And what process was?
28 nanometer FDSOI.
Cool.
The predicate registers reminds me of Itanium. I was not sure why you're using the predicate registers, because you don't have control divergence problems.
So I'll go back to the TX2. So these activity flip-flops are those mask bits. So the reason is you don't have any control flow. So in a data parallel machine, simple vector machine, you need to do conditional execution. That's why you have predicates.
Peter Shu, Oracle Lab. For the strided loads and stores, are they indices or pointers?
For the strided one, it's just a constant interval in bytes. For the indexed,
Yeah,
yeah, for scatter gather, they are just byte offsets. So you have a scalar base, and then you have byte offsets. So the addressing mode, go back to that slide. So index has a scalar base and a vector offset, and both are bytes, byte addresses.
Hi, Tommy Thorne, unaffiliated. Do you have any support in GCC, or how's the toolchain support coming?
Sorry, say again, I didn't quite.
The question of compiler support for this.
Oh, compiler support. So like I said, we're focusing on compiler support for XWatcher for now. There's a lot of code lying around internally for LLVM, auto-vectorization, as well as OpenCL mapping to XWatcher. It'll take a little while to bring that out. We're still working on the V extension. This hasn't been defined, but XWatcher is sort of more actively being worked on with compiler support for that. A lot of the compiler stuff will port over pretty easily to V.
John Liddell from Texas Tech. Do you have support for vector reductions and vector reductions under mask?
You will be adding things like that, yeah. There's a question of how much of that stuff. Well, vector reductions, the usual way people want to do that is just with providing instructions to move elements around in vector registers. So we'll have some way of doing register permutes, which will then be used. On top of that, you can build the reduction operations.
Guy Lemieux, Vector Blocks Computing. I really like seeing the mixed width support for different size operands. But what I'm seeing is inability to scale. The vector register file is a fixed amount of data in an implementation, and you're tying that to the ISA. And so if you port your software to, or you want to run your software on another implementation with a larger vector register file, there's no automatic way to take care of using that extra storage space. And that can become a bottleneck in your parallelism.
No, I mean, that's part of the ISA. It doesn't care how much physical register storage, use all of it. The only constraint is only 32 architectural registers. The length of them is open. You can have them be a zillion long, and the ISA would still work.
Yeah, it doesn't, you can use a more scalable approach. You don't have to encode the number of you don't have to have a fixed register file like that. You can have a bank scratchpad instead, and then it gives you arbitrary number of vectors, not just 32. We can take that.
Yeah, we can
offline
have a
and I'll
scratch.
show you.
Other work is we have scratch pads also, but for efficient control and hazard clearing, you want small names for operands, which is why vector registers are good.
You can still do that on the addresses themselves. It's quite efficient because it's just in the scratch pad. It's a small, narrow 14-bit field comparison.
Sure. Okay, good. I think that means it's lunchtime. Okay. Oh, Andrew.